Picking up where we left off, we're talking about finding the antiderivatives or integration, figuring out what functions have the derivative that's equal to the function we're trying to integrate. We're going to do a couple more polynomial problems just so that you can do these more easily with more practice. So we're integrating the function of x plus 2. Now remember, just like with differentiation, you can think about integrating each part separately. Like you can integrate x and then integrate 2. Remember that dx is very important, so it might seem tedious, but continue to write it. It's our variable of integration. Then you can look at integrating each of these separately. You can think what function has a derivative that's equal to x and 2, or you can use that polynomial rule we learned in the last video, is everything is the opposite of finding the derivative. So the last thing I did for finding the derivative will be the first and opposite thing. So instead of subtracting 1 from the exponent, I'm going to add 1 to the exponent, and there's already 1 there. And you can imagine there being an x to the 0 here, so you would add 1 there as well. So this would be x to the 0, and that would be x to the first, so it would be x squared and 2x. Then if you think about the first thing you did for finding the derivative, that's to multiply the exponent to your variable. Now we're going to divide it, the new one, and that's just 1. And then you can simplify these. This is just going to be 1/2 x squared plus 2x, and then we always have to have that plus constant there because we're still looking for general solutions. Down here we'll look for particular solutions. Go ahead and try B on your own. Pause the video, try it, and then come back to see how you did. And then I forgot to put the integral sign before that, but you're integrating it, and you just add 1 to these exponents across the line, and then divide by that new exponent. So I divided by 5, by 3, by 2, and this is my new polynomial with the plus c. So that is the general solution for that particular integral. Now we're going to look at particular solutions, initial conditions. So a particular solution, first of all, let's go ahead and define that. It's an equation to a specific function from its family. That says family right there. Right, and that's, you learned back in algebra, the family of functions. So x squared plus 1, x squared plus 2, x squared plus 3, x squared plus 4, where x squared is your parent family, and all of those other ones are a function of that particular parent. And then initial conditions, and a point that you want that solution, that graph to go through. Like we see down here, here's an example of a family of function, but then we have this one point right there that we want our graph to go through, and that point is our particular initial condition or solution. Well, the solution would be the equation. The point is the initial condition. So let's put that into practice. So first of all, let's go ahead and integrate this function of 1 over x squared and see if you can't figure out how to use that point 1, 0 to find the particular solution. Pause the video, try it, and then come back. When you integrate, you should get -1 over x plus c. And this, you have to remember what you're finding. You're finding the original function, right? We were given the derivative, we integrated, we found the original. So that's where we can put in y equals -1 over x plus c. And since you're given the point 1, 0, remember this is a coordinate, this is your x value, and that's your y value. So plug them in for your x and your y. And when we do, you go through and solve, and you get c is equal to 1. Now we're looking for the particular solution, so we plug that back in up here with our c and our particular solution given that initial condition. We want the graph that goes through 0, 1. That equation matches that graph right there. Okay, so that's your particular solution. If you have an initial condition, that's how you find that c in the plus c part of that formula. Now we're looking at this problem. It says a ball is thrown upward with an initial velocity of, let me get that little, 64 feet per second, right? So that would be your v sub 0, v sub naught, and initial height of 80 feet. So then that is your h naught, or your h sub 0 at time 0. Find the position function. So the position function is typically given as s of t in most textbooks, given the height as a function of time t. So height as a function of time t. So if you think about the equation for free fall, right? It's going to be something like negative 16 t squared plus the initial velocity times t plus h naught, or the starting height. Okay, so that's the free fall. That negative 16 represents the gravitational pull. And see what you can do from here. You're finding it, plugging in the variables, and seeing what we can do. Pause the video, try, and then come back. Here is our position function, right? And its height as a function of the time. So the height is the function, time is the variable. That's what we have there. Now let's take a look at part B. It says, when did the ball hit the ground? Don't look at the graph at the right. If you have a copy of these notes, don't look at the graph at the right. Think about what is happening when the ball hits the ground. Well, the position is 0, right? So in order to find where the position is 0, we are going to set the position function, which is the one we just had, equal to 0. So it would be the negative 16t squared plus 64t plus 80 equals 0. And you can graph that on your graphing calculator, but you're actually going to get two answers. You notice here one is at 5, and the other one over here is going to be at negative 1, because that graph continues to come down. Okay, but the negative 1 is irrelevance. That would be negative time, which can't exist. So we're going to have to just look at the 5 seconds. All right, so you notice we didn't use any calculus there. We didn't have to, but if we wanted to know when the ball, like for example, if we want to know when was the ball at its highest point. Now this is something you already know, because if you think about the speed, you don't know what the height is, but the speed of that ball, right, to find that point, you would just find the derivative and set it equal to 0, because when that ball stops and turns around and starts coming back down, it stops moving. All right, so just like when we're finding your maxes and mins, relative extrema, to find those relative extrema, you would set the derivative equal to 0. And if we were to do that, you would find that at t equals 0 and height is about 140, it looks like, is what you would get. Okay, so just remember that as you're working through some of these problems, it's the same as the extrema for a lot of these story problems, especially with free fall. Think about what the derivative, setting it equal to 0, will tell you. Even sometimes the second derivative, what that will tell you, the points of concavity, why are they important in this problem. Just kind of think through the problem, understand the problem in terms of the first and second derivatives. Okay, that is it for this page of notes. That's all you need for this section, introduction to the integration. Next section, we will talk about applications of the area in integration.